hello, good afternoon, and welcome to this keynote presentation. I have the pleasure to introduce Professor Giorgio De Pasquale. He's going to deliver a keynote presentation entitled Development and Integration of Additive Manufacturing Lattice Structures to Reliable Technological Solutions. Professor De Pasquale is Associate Professor of Machines Design at the Polytechnic di Torino in Italy. He has about 15 years of research experience in the field of smart structures and systems, including micromechanics, human-machine interfaces, energy harvesting, and of course, additive manufacturing. Professor De Pasquale, who was a visiting researcher at MIT and the University of South Florida between 2009 and 2013, as active projects with research institutions in Europe, Japan, and United States, received several awards and published about 80 scientific papers and 50 patents. Professor De Pasquale, the floor is yours.
Thank you very much, Mr. Chairman, for the introduction. This keynote speech is has the goal to sum up our activities about the design issues related to lattice structures fabricated by additive manufacturing processes involving metal materials. So as we know, lattice structures are defined by the repetition in space of cells in 2D or 3D dimensions. And this kind of structures had a large spread thanks to additive manufacturing processes in the last years. They provide some important benefits in the fabrication of mechanical components and biomedical components, like the very high ratio between strength and weight, a large surface for thermal exchange, the favorable capabilities for adhesion with other tissues and other materials, and also are prone to support different functions, so to fabricate multifunctional devices. We have some consolidated applications in the biomedical fields, like scaffolds, prosthesis interfaces, or interfaces for exchange of heat between gas and fluids. Anyway, there are several open issues in the mechanical design of lattice structures, and our activities are addressed to provide some methodologies to solve the main issues and to provide smart and fast ways to design and fabricate lattice structures. Main open issues are related to the qualification and the standardization of processes, and also to provide some dedicated tools for design and simulate lattice structures that are not always the same tools already used for other mechanical applications. Another important issue is related to the lifetime of a mechanical, let's say, lattice structures applied to mechanical fields, or where you have variable loads in time because of the accumulation of life cycles. And last but not the least, the problem is the management of CAD files that sometimes is complicated by the dimension of these files. So just to have a fast idea on the lot of parameters, process parameters affecting the mechanical design of lattice structures, here I listed the most important of these parameters. Some of them are related to the laser, some of them related to the scanning performances of the laser over the powder bed. Other parameters relates to the powder properties or temperature management. So we have a huge number of influencing parameters that changes the mechanical properties of the component. We have to find some way to manage this wide range of variability to find a repeatability of design and fabrication. We are using several industrial and academic equipment to provide the best reliability and repeatability output of our processes in order to get confident to get confidence from our results. So not to have large variability of results depending to the supplier of lattice structure. That is one of the main issue up to now. So we are using SLM processes, EBM processes, laboratory facilities like microscopes, other tools for the mechanical characterization, optical characterization of our samples. So the first point is to stabilize and to calibrate, let's say, the fabrication process. To do this, the best way is to find what is the correlation between one process parameter and one mechanical property, and also the mutual correlation and interaction between the process parameters. For instance, we can understand some problems looking at these pictures where we have dimensional errors between horizontal and vertical struts, or irregular shape of downskin or upskin shape of our structures. So by using statistic tools like design of experiments or analysis of variance, we are able to fix some significant parameters of our process. For instance, here on the left, we have 3 variables: laser speed, downskin thickness, and volume energy density, and several levels, high and low level of each one of these parameters, and try to find what is the correlation between the parameter and the output results, and what is also the mutual correlation between the variables together, one respect the other. The same thing is valid also for the density and the porosity of the material, which is also related to the parameters of the process. We know that high porosity means low mechanical properties. High porosity on the surface associated to the contour settings of our process means low fatigue strength. And again, so from a mechanical point of view of structural design, we need to understand which parameter affects which specific topological property of our structure. By moving towards the mechanical behavior of lattice, we have 3 different levels of analysis. The properties of the parent material, of course, these properties depends to the process, depends to the growth direction inside the fabrication, the additive manufacturing machine, depends also to the size effect, depending so to the dimension of the sample. In another scale, that is the micro scale, we can investigate the properties of lattice, so the properties of the single cell, by using especially theoretical analysis or compact modeling. And in the last scale, the macro scale, we can understand the behavior of the full structure and the interactions between cells. Here, we can also apply experiments to validate the previous models. So the parent materials can be studied by means of mechanical tests on specific samples, designed depending to the orientation in the fabrication machine, or depending to the process parameters, and of course depending to the material used. For example, we have output curves like this. Just to have an idea about the importance of the process, the same material can express completely different behavior, ductile or brittle behavior, depending to the process. In this case, we have titanium alloy subjected to run with SLM process on the top line and run on EBM process in the lower line. We can see very different behavior. So just to underline that the process is determinant in this case. The same thing is reported by the breaking surface of samples. We have 45 degrees breaking surface orientation, typical of ductile materials in the first case, the left, and the 90-degree orientation, typical of fragile materials on the right. About the structure, so after the combination of different cells and fabricating a structure, we can investigate these properties by means of parametric samples. That means that these samples have different cell size or shape, and we can control the influence of each geometrical parameter on the results, and we can compare these results with the predictions provided by models. On the top left, we have an example of layout of our machine chamber filled with samples, different kind of samples with different orientations. Then the printed samples, the release samples, and on the lower line, we have two frames of compressive test and shear tests on lattice structure samples. Of course, here also we have other influences on the results provided, for instance, by the post-printing treatments, thermal treatments on the process, on the samples. Here again, we have collected some frames of our compressive tests on cubic cells in titanium alloy material. This is a sample represented by a cube, 40, 50 cube millimeter sample. The maximum force applied is 70,000 Newton of compression, so a pretty high force. Another example of another kind of lattice structure. Here we have BCC cell, body-centered cubic cell in steel. The same shape again of the sample, 50 per 50 per 50 cube millimeter. Here we have different shape of cell, but also different thickness of struts. Just to have an idea about our approach, that is to investigate and to cover different cases of dimensions and shapes of the lattice to provide the validation of predictive calculations, let's say. In case of a macro scale test results, we have diagrams like this. Each peak corresponds to a collapse of a single layer of our sample, and every peak also reports the thickness and the stiffness, mainly of each of the residual layers survived in the samples. So in a diagram load displacement, we have a behavior like this. In a diagram where we plot the stiffness of the single layer, depending to the number of collapsed layers, we also observed a trend like this, testifying that a progressive lowering of stiffness during the collapsing of each single layer of a lattice structure. Another important result from our test is the mode of failure. In this specific sample, we observed, for instance, three main failure modes. Mode 1 is associated to a buckling behavior, so instability behavior of vertical struts. In the mode 2, we have a bending behavior of horizontal struts, so plastic failure. And the mode 3 is a combination of mode 1 and mode 3. Here we can also see that the line of fracture of break of our sample follows the shape of cell. So in some way we are also able to modulate the direction and the way of crack of our sample by changing the shape of and the distribution of cell in the space. Something about the modeling of lattice perform mechanical behavior. There are different approaches. The analytic model is the best one in theory, because it allows to clarify the specific relations between the parameters. Because in analytic models, you can write the full explicit equation that describes your behavior of your cell. And analytic models are based on the theory of the beam theory that structural engineers well know. But unfortunately, only simple shapes can be treated with analytic models. In case of complicated shapes of cells, it is quite complicated to describe equations like this, for example, that is valid for the cubic cell, where we have different components from Euler-Bernoulli theory, Timoshenko beam theory, and so on. So for other more complicated cases, we need to use numerical models. And here again, we have at our hands the traditional finite element modeling tools that can be used, of course, but they complicates a lot the calculation because they introduce a very huge amount of equations in our solver system, because we have a complex geometry, so high number of elements and nodes. And so this approach is not very feasible for complicated and large components. The alternative, that is the best way in our opinion, is to use some different models that are reduced order models, where, for example, the homogenization method, where you can replace the complex shape of your lattice cell with an homogeneous solid with very simple geometry that has the same mechanical and structural properties of the real lattice shape. There are well-known methods to do this transformation under specific hypotheses. And basically, we can apply a strain field, impose a strain field on the representative volume element, that is our cell, to write 6 equilibrium equations and to calculate the stiffness matrix of our element and each component of the stiffness matrix. Then, by calculating the compliance matrix, that is the inverse of stiffness matrix, we can simply calculate the properties of Young modulus, shear modulus, and coefficient of Poisson of our element. And to use this brick, let's say, very easy and simple shape to make our models in a very, very faster way with very low computational heaviness. For example, in the case we see before, for the cubic cells, we can study only one representative volume element and study this behavior and then extend the properties all over the volume. The results in this table on the far right, we can see that the errors are pretty low. And these errors also includes the border effects of the samples that are quite small, so these effects are quite important. Something about the importance of lattice structures in application for biomedicine, thanks to the functionally graded geometries. This way of design includes the variation of the cell geometrical parameters inside the volume of the component. For instance, we can increase the density of the equivalent density of the cell by changing the position. This allows to create transition regions between bulk volumes and lattice volumes, and allows also to create hybrid structures. For example, in the coatings of prostheses, it is quite useful to improve the adhesion between bone tissues and to have a gradual variation of stiffness that allows the bone to training itself for improving the anchoring. The same thing is also used in literature for reproducing biological tissues where the density is variable. For example, in a femur with a CT image, you can understand where the density is high and low, and to reproduce the same by using different densities of the lattice structure. What about reliability of lattice? This is a quite important topic for mechanical design, because a strong structure in static may be very, very unreliable under cyclic loads. So we need to understand what happens if you apply cyclic loads to the lattice structure. We have a lot of notches, a lot of corners that are potential points of initiation of fatigue cracks that may induce the breaking in very short time. We have 2 approaches to investigate this. We can estimate the lifetime of our component by modeling or by tests and failure predictions. Let's start by something about modeling. If we consider a lattice structure where a cyclic load is applied, the shape is complicated, so it's not easy to use FEM models. It's quite complicated. So the best way is to apply the homogenization method to convert our lattice cell into a homogeneous solid material, so a brick element. then to compose, to rebuild our volume, and to understand, to calculate the stress distribution inside it. Then we can identify only the most loaded cell. We don't care to study all the cells, only the most loaded one is enough. We apply the inverse homogenization criteria on this most loaded cell to rebuild the original shape of the real lattice cell, and we can investigate the stress distribution on the most loaded cell of our lattice structure. Then we can simply apply multi-axial fatigue theories that are well known and largely applied in mechanics to understand the number of cycles to failure depending to the load applied. That means depending to the average load and depending to the amplitude of the variable load applied. So this is a reliable, fast, and suitable way to understand lifetime, to predict lifetime in lattice structures. From the experimental side, we have different approaches. Here I show only one, where you can see some samples in uniform shape or graded shape. In this case, we applied a cyclic load at 30 Hertz on these samples, and we simply measure the number of cycles to failure of our samples, and we try to reproduce the same behavior that we can see for traditional study of mechanical fatigue in mechanical components. The first results we have are promising because the shape of our output curves are very similar to Wöhler diagram, and so in some ways we can use the same tools we already know. Another approach, for example, is to induce some failures on our lattice structures and to modify the global stiffness of the structure. In this case, we can use the structural dynamic response to predict the moment of catastrophic failure. And in fact, if we see the dynamic response of this sample, where we have damaged artificially some rows of cells, of course, we can see that the response varies. The resonance peak is moving. So we can also define a warning threshold and an ultimate breaking threshold that can be considered to replace the structure, or even to stop operations, and even to prevent the failure. I want to conclude with two applications quite new of lattice structures. The first one is composites based on filling lattice structures with polymers. This technology is pretty new. We tried to make these samples with good results by creating a temporary mold made in silicon, and by filling our lattice structure. In this case, it was a metal lattice structure made with aluminum, with liquid polymeric resin, followed by a curing. So what we get is a polymer with a sort of reinforcement inside, provided by the lattice structure. A specific equipment is needed to do this, but the very interesting thing is that is reported here on the left, where we have the force displacement curve of the pure lattice, the black line, only lattice, then only polymer, the dashed lines. We have two dashed lines because we tested two polymers with two different hardness. And the gray lines are instead the composite material. So the result is that the energy, elastoplastic energy absorbed by the composite is higher than the sum of the two energies absorbed by each of the two components. And this increase of energy absorption, as we can see in the right, can reach also 70%. So it's a pretty high increment of energy absorption that makes this composite very suitable for impact absorption applications. The very last one thing is the functionalization of lattice structures. In this case, we are using a coating of our metal parts that is based on a lattice coating, to create a smart joint with carbon fibers polymers, so with composite polymers based on carbon fibers. We provide a mechanical connection between the carbon fibers and the lattice cells in order to improve the adhesion of the two materials to create a functional joint without adhesives or rivets or mechanical connections. And this is very useful for lightweight applications. It's useful because speed up the process of joining metals and composite materials and reduces the pollution related to the adhesives and chemical agents used for the adhesion. Two applications have been already studied. One is for ultralight wheelchairs, where we designed a component on the backrest to fix the backrest with this functional joint. And another application is associated to food prosthesis, where again we calculate and dimension this functional joint with the upper connection of the prosthesis in carbon fiber material. So just to conclude, I try to give you an overview of our activities based on additive manufacturing lattice structures from a mechanical point of view. Of course, the conclusion is that a strong design method involves modeling and simulation from one side and experimental validation from the other side. Our results are based on investigation of parent material properties, on the prediction of single-cell properties, and on the global lattice response of the structure. Yeah, a very important focus is put on the reliability and lifetime of lattices, because it is important to provide some way to predict the failure and to anticipate the failure, especially when these structures are applied on the body or inside the body. And of course, some new ideas that have been shown that are based on polymers filling for impact absorption and smart joints between metals and carbon fibers reinforced polymers. Thank you very much for your attention.